I'm I I keep posting the recorded video on YouTube channel. So if you want to watch it again, you may not. So so please feel free to watch again. Okay. All right. So in the last class, we talked about the dimensionality reduction, and then I showed you the how principal component analysis actually works, right? So anybody can say why dimensionality reduction is important? Any idea? I think Jihao wants to say.
Maybe we want to reduce the noise in your data set, and we want it to be more easier to interpret.
Uh-huh. Yeah.
And
And so
and
yeah, and
uh, and reduce noise easier to interpret. That's what I have for now.
okay, I think Kevin wants to add something. Do you want to add something, Kevin?
No.
Okay. So so in the real situation, if you have a lot of data set, first of all, you know, the theoretically more predictors would improve your model performance, right? So the more you enter your predictors, the UR score will go up. But in reality, so a lot of variables that will have a lot of noise, the measurement error, right? So sometimes it could decrease model performance. So we want to get the best predictors to present the best model performance. So that's the first reason. And the second reason, so it's easy to understand and easy to communicate with other people, right? So that you can visualize with the 2 or 3 principal component analysis, the principal component scores, but you cannot visualize 10 variable. That's a 10 dimension, right? And also sometimes that you want to develop a more parsimonious model, right? The more variable, the lot of a variable doesn't make sense, doesn't guarantee the best model. So we want to reduce the dimension for the further analysis. So let me briefly overview. So here, dimensionality reduction, right? So we talked about the dimensionality reduction. So there are 2 different approaches. The first one is variable selection, right? This is the first approach. The second approach is variable extraction, right? So for variable selection, we can simply apply, backward regression analysis or forward regression analysis or stepwise regression analysis. So in that way, we can try to select or remove important or unimportant variables, right? So also more advanced method is like a ridge regression or lasso regression or elastic net regression. So these regressions, they actually give some penalty for unimportant, give penalty to unimportant coefficient predictors. Okay, so these are more advanced approaches. So we will not talk about these approaches in this class. The second is the variable extraction. So first, we talked about the principal component analysis, right? So principal component analysis. And the second one is, so the partial least square method. So partial scale least method is pretty similar to the principal component analysis, but partial least square, the difference between principal component analysis and partial least square is that the partial least square is to develop a model, another model based on the measurement error, so like the residual errors. So it incorporates some residual errors. Okay, so this is more advanced method, but we will not talk about the details in this class. And then you can see third one is the factor analysis, right? So in this class, we learn about this one. In the next class, we will learn about the factor analysis. Okay. And then I will talk more. Can I erase this one or? Okay. Let me erase a little bit. Okay. Okay, what is the difference between principal component analysis and factor analysis? So basically they are very similar each other. So we can think about a couple of difference. So first, structure, they use the different structure of variance. Okay, structure of variance. Basically, this is total variance. Let's say this is total variance. So the total variance is composed, it consists of some common variance and unique variance. Okay, so common variance is the variance explained by model. So it is like the R square. Okay, so and the unique variance is the variance which is not explained by model. So this will be a residual variance in the regression analysis. Okay, and then unique variance is also divided into the specific variance and error variance. So error variance is more like the measurement error. Okay, so this is a random, but if you have some systematic errors, there will be systematic variance. Okay, so usually we have a common variance and unique variance. But PCA, in the PCA, there is no unique variance. So in the PCA, total variance is all common variance. Okay, so it does not take into account the unique variance part. So it just consider the total variance is the common variance. Okay, so here is the total variance. This is total variance, but it consider, okay, total variance is common variance. Okay, and also it only allows orthogonal, right? Orthogonal, the rotation. So every principal component will have orthogonal relationships among principal components, right? So it doesn't allow of rotation. Okay, so and then because it considers it treats total variance as common variance, so which means it does not take into account any error. So measurement error. So it considers all the predictors are perfectly reliable. Okay, so that's why it is used for observable variable, observed variable, not latent variable. Okay, but EFA is, in EFA is total variance is equal to common variance plus unique variance. Okay, so EFA analysis takes into account any measurement error. So EFA analysis considers all the predictors or outcomes are not perfectly reliable. Okay, so total variance. This is total variance. This is common variance and unique variance, right? So, and then it allows rotation. Even though we rotate the principal axis, it can still remain the original, the variance of each axis in EFA analysis. And also it is used for latent variable. So PCA, so to run the PCA analysis, what was the first step? We need to normalize our data, right? So we need to normalize our data. So make it normalize, standardize it, and then get the covariance matrix. That covariance metric is a correlation matrix, right? So if you get the correlation matrix, diagonal is all 1, okay? And this is the variance of a correlation matrix. And then we just assumed the variance is 1. So which means, okay, the total variance is 1. Total variance is 1, but everything is common variance. Okay, in PCA. But EFA, instead of using all 1, we are replacing the diagonal using commonality, so R square of each value. So it can be 0.8, 0.7, 0.989, 0.99, okay? So instead of using 1 in the diagonals, we use commonality for the covariance matrix and correlation matrix. So in that way, we can take into account the measurement error. This is more like a regression analysis and CFA. So regression analysis, think about the regression analysis. Regression analysis doesn't take into account the measurement error, right? It assumes that all measures are perfectly reliable. So if your predictors are unreliable, so in other words, the reliability is really poor, so your prediction models will be biased because your prediction models will include a lot of measurement error, which is not explained by your model, right? But EFA or CFA, those are the latent model, so it takes into account the measurement error part. Okay, this is a fundamental, the difference between these two approaches, the PCA and EFA. So we'll more talk about the EFA later, but this is the general overview. Okay, any questions? Okay, so okay. Can you make a mute? So I think somebody didn't mute. Okay, thank you. All right, so okay, now let's talk about, so before I show you the R example, let's see an overview of PCA algorithms one more time. So for step 1, we normalize data with a mean 0 and 1. And then also we compute the covariance matrix of original variables. right? So in that way, we can get the correlation matrix or covariance matrix. And then compute eigenvalue and eigenvector using the correlation matrix, right? And then find and then order the eigenvalues and corresponding to eigenvectors. So if you have a 5 variables, then we will have a 5 eigenvalue and eigenvector, right? So highest eigenvalue will present the largest, the first principal component that explains the most of the variance. So Z1, right? And then these coefficients will be eigenvector of the first eigenvalue. And the second principle, this is eigenvector from the second eigenvalue, right? And in that way, we can develop the principal component, the equations. And then x1, x2, and x5, these are all the data set. If we enter our data into this equation, we will get this score. That score is called principal component score. And then we can use this score instead of raw data. Okay, so let's look at, I posted our example on the Blackboard. So first, I will import my data set. So in this example, I will use some body fat, the data set. So first, I'm going to load this data using the CSV, read that CSV, and then let's check our names. So that you can check your names using the names function. Name, okay, here. So this data contains body fat. Okay, this is our outcome variable, and then weight, chest size, abdomen, and hip size, and thigh, and biceps. So our goal is to predict body fat ratio using these predictors. Okay. So, and then let's check structure of this data set using str structure. Then if you run it, so, okay, now we have body fat. This is data frame and 251 observation. And we have 7 variables, and body fat and weight, chest, they are all numeric values, right? And then using a head function, I'm going to print the first 6 data set, body fat, weight, and chest, right? And if you want to see your whole data set, you can type a view, okay, body fat, and then run it. So now you'll see this is a whole data set, okay? So I know some of you may not be very familiar with the R, so I will try to explain, as detailed as possible. So first, okay, we have how many variables? We have 7 variables. Let's check the correlation first, okay? So core function, and then we want to check the correlation, body fat data and correlation, and then I saved this one to my core variable. You can use equal sign or you can use like this, okay? Doesn't matter. And then run it, and then I will print the correlation matrix. Okay, this is correlation. Let me this correlation matrix. As you can see, we can see very high correlation among variables, right? It's very high. It's actually 0.92, 0.88, 0.74, right? So if you have this kind of data, so definitely we have to worry about multi-collinearity problem, right? So it will really distort the power of our analysis. So, and then you can check the patterns using plot function. So like plot, okay, I plot it, let's zoom it, so you can see. Okay, now we can see so all the positive patterns among variables. Right. Then here is a core plot package. If you install the core plot package and then load your core plot, and then if you run it, and it gives you some this kind of output, it's much easier to read, right? So these colors, the red color represents the negative relationship, and blue color represents the positive relationship. This is a correlation from 0 to 1. Okay, dark blue represents the very strong relationship, and dark red represents the very strong negative relationship. If you look at that, so the diagonal is all 1, and then we can see a lot of blue correlations that they are fairly dark, right? So we can see, okay, there are a lot of that there are high correlations among variables. Okay, now you can check the eigenvalues. Okay, so this is a correlation matrix, right? And then this is eigenvalue from the correlation. And then I just extract only values. Okay, so it will return the eigenvalue. Okay, and if I run it and then save it to the eigen, and if I run it, and then it will give me eigenvalue. Okay, so we have 1, 2, 3, 4, 5, 6, 7 variables. So we have 7 eigenvalues, right? So if you look at this, the first eigenvalue is 5.57, and the second eigenvalue is 0.65. So these results that clearly shows us, so okay, there might be some multicollinearity issues. Okay, because these 7 values are explained by only one principal component, the one eigenvalue. So they are very strongly related to each other. Okay, so this is one indication. And then you can get the ratio of maximum eigenvalue to minimum eigenvalue. Okay, so this is a maximum eigenvalue. It's 5.716, and this is minimum eigenvalue, 0.04. And then we can get the ratio. So ratio is 120. So rule of thumb is 100. Okay. If this ratio is greater than 100, that is red flag about the multicollinearity. Okay. So, and then kappa coefficient. Here is a kappa function. It gives us the same information. This is correlation matrix. Exact equals true. It will return the number, exact number. So if you run it, okay, now we get the same number, right? Okay. So kappa coefficient. So this will give us some, the multicollinearity issue. So, and then now let's look at the VIF. So you learn about the VIF, right? Variance inflation factor in the regression analysis. The rule of thumb is 10, right? But if any VIF is greater than 5 is a concern, right? If any VIF value is greater than 10, it's definitely the multicollinearity issues. So to run this one, I save the car package and then save it, and then run model, linear model, dependent variable, and then I put that here. So that means I will enter all predictors. Okay, so in the data set is body fat, and run. And then let's look at the VIF. Okay, so here's VIF values. Weight is the 13.88 is greater than 10, and chest is greater than 5, greater than 5, greater than 10, 5. So this results clearly shows, okay, there are very high correlations among variables, right? And then also you can get the mean. Mean VIF is 8.22. Okay, so we have 7 variables. They're having very high correlations. So now, which means you can take the 2 different approaches, right? First, you can extract component, principal component based on these correlations, right? Or you can reduce the number of variables. Some variables are very highly correlated each other, right? So let's do the first approach, the principal component analysis. So principal component analysis. So body fat data has all, this data set includes outcome and predictors. So I will just get the predictor part, okay? So first variable is outcome. So I will remove the first column. So this is row, nothing in the row part. So which means I will select all the row, and then I will remove a first column, and then I will save this result to the X. Okay, so this will be predictor. So you can do that in this way. Okay, so you just simply select, instead of removing first column, you can select the second to 7 columns, right? And then now you can run a principal component analysis using PRComp function. Okay, so body FX, right? So this is our predictors. So we don't need to run, we do not want to add our outcome variable here, right? Because we want to extract the principal axis based on predictors. So I'm only using predictor, and then center equals true, which means we will center our variable as 0. Okay, and then scale equals true. This is standardized. Okay, so normalize. So if you if you put the center equals true and scale equals true, that means we will standardize. Okay, and then I will run this one. Okay, and then we save this result to here. Okay, and then and then I will plot it, plot this result, and then type L is line. Okay, so if I run it, okay, so it will give us this script plot. Oops, where is the script plot? Right here. So this is number of components, right? And this is variance, right? So variance of each component is what? No, what I'm saying is the variance of each component is eigenvalue, right? So the first component eigenvalue is a 5 point something, or yeah, a little bit over 5 point something, right? So it has very high eigenvalue and dropped it significantly. And then second, right? And then the second eigenvalue is less than 1. So maybe this is negligible, right? And then third is is still negligible. So we can see an elbow plot here, elbow point. It dropped again and then gets flattened, right? So generally we find the principal component at the elbow point, but this elbow point to PCA is the variance of a second PCA is quite small. So maybe you can choose one principal in this case. Okay, or no, if you can justify your reasoning, you can choose second, right? So, but I would choose the 1. So then let's get the summary of this PCA result. So this is the PCA result. So this is standard PCA, first PCA, okay, second PCA, third, and to the 6th. And then this is the standard deviation of each principal component score. Okay. And then this is a proportional variance, which means this first principal component explains 83.9% of your total variance. That's a lot, right? So, and the second principal component explains only 7%. And third principal component explains 5%. And the fourth is only 1%, or 1.6%, 1.4%, and almost 0%, right? And this is cumulative proportions. So this total variance is 1. And then second principal components explains 91%. Principle 1 and principle 2 explains 91%. Okay. All right. And then we want to get the rotation matrix. The rotation matrix, this is the PC loading matrix. Okay. So using the body fat dot C. So this is, we just run the PCA result, right? And then if you put the $ and rotation, it will print our principal component equations. This is principal component equation. So how can we interpret it? So PC1 is equal to 0.433 times weight plus 0.409 times chest plus the 0.409 times abdomen plus 0.42 times hip and 0.39 times thigh plus the 0.37 times biceps. Okay, so this is the first principal component equation. The second equation is like, okay, negative 0.03 times weight minus negative 0.2 times chest, blah, blah, blah. Okay, so this is each principal component's equations. Okay. And then now you can get the principal component score using X. Okay, these are all the built-in function in the PCA. PR comp analysis. So if you run this one, oops. Yeah, no. Okay, so this is PC1. I only printed the first 6 observations. So this is the principal component score. Okay, so this is the first observation, second observation, third observation, fourth observation, sixth observation. This is the principal component for the first principle and second principal component of the second principle and third principal component of the third principle. Okay. So if we select only 2 principal components, we will use these scores for the subsequent analysis instead of raw data. Okay, this is principal component score. Okay. Now let's get the correlation between these principal components. So principal component analysis is orthogonal, right? So we expect, so this metric should be, the correlation should be 0, right? So we will run the correlation. Now you will see a lot of scientific notation, but I will round it to, okay, which means I'm going to round 2 decimal point. And if I run it, okay, now you can see, right? They're all 0. So which means that they are all orthogonal. Okay, and the diagonals are all 1. Right? Which means, okay, so this is total variance. So total variance is all common variance. Okay. So there is no the unique variance in this part. Okay. So now let's get the, now we can get the correlation between like this. I will get the correlation between PC and this is the PC, our principal component score. And then this is our observed data predictor. Okay, this is a predictor, right? So from the body fat data, I extract first, I will remove the first column, which means this is all predictor. And then this is a body fat score. So this is the principal component score, right? But principal component score, this is not the data frame format. So I transform it as the data frame. And then I combined these two values, two matrices, two data frame into one. And then get the correlation. And if I run it, okay, now we got it. So maybe we can round and round to. Okay, wow, it's pretty big. So you can see these are the correlation metrics between predictors. They are highly correlated each other, right? And then you can see this is a PC1, PC2. The PC1 score is very high correlation with the first predictor, right? And then, but there are very low correlation between PC2 and PC3. Right, and PC4 is pretty low correlation. Do the same thing. So PC1 is highly correlated with the second predictor, and this correlation is very highly correlated with abdomen, right? So you can see PC1 has very highly correlated with all the predictors. But PC2, PC3, PC4, they're fairly low. Okay, so we can check it. And then now let's make the data set. So I combined predictor and then principal component, and I combine it. Then I save it to the bodyfat.pca. Okay. And then if you run a bodyfat.pca, it will give us this score. Oh man. So holy moly. So okay, so it says that there is no variable name here, right? So PC1 is a variable name, so there is no variable name here. So I just want to add a variable name as a body fat. Okay, so I create a body fat as this first column's name is body fat. Okay, I save it. If I run it, so now we can see it's a body fat, right? So in that way, we can create the body fat name, right? So now let's look at the correlation matrix, showing the correlation of a body fat for each principal component. So we already looked this one. So this is the body fat. This is our outcome variable, right? So outcome variable is highly correlated with the first component, but negatively correlated with the second component. And the third component is not very high. And the fourth component and the fifth and sixth, maybe third component and sixth component is not highly correlated with our outcome variable. Okay. Does that make sense? Okay. So even though we have a 6 principal components, you can choose single principal component. But if you want to add more components, that you can see the correlation between outcome variable and the principal components scores. Okay, maybe second component and the sixth, maybe fourth component is still highly correlated. Not high, but it's pretty fairly correlated with these two. So maybe we can add this one in the further analysis. And now let's plot the PC1 and PC2. Let's say we extracted 2 principal components. Okay, so and then you can plot it using the first principal component score, the second principal component score. So this is principal component matrix and the first and second column. And get the correlation. And then you can add vertical line and horizontal line. Add it. And then now you can see it. Okay, maybe this is the principal axis, right? So this is maybe I will add X label equals PC1, Y label equals PC2. Okay, now we can see. Okay, so this is the PC1 and this is PC2. Okay, so the data point, so definitely we can see the PC1 has larger variance than the PC2, right? So if you want to check the graph, PC graph, you can plot like this. Okay, and then now we will see some PCA. So Factor Extra, the package, this provides more advanced graph visualization for PCA analysis. So I will install a library, and if I get the PC, so this will give us the script plot. So this is dimension 1 to 6, and this is proportion percentage of explained by variances, right? So the first principal component explains 80, maybe 80 point something percent, and then dropped it. This is pretty similar to the script plot, okay? And then also you can make a graph using F visualization underbar PCA.individual. So it will return the individual data point in the PCA, okay? So this is the PCA function, and then these are all the options, okay? These are all options. So color, gradient color, and a color individual. So these are all options that you can see more information from question mark, and then run it from here. So visualization principal component analysis. Okay, so here is the graph of individuals, the graph of variables, the biplot, individuals and variable. They're all different options here. Okay, you can find the options, but I will run this one. Okay, how can I? All right. Okay, if I run it. Oh. Give me a second if I run it again. It takes some time. Okay, it's running. What is that warning message? Yeah, okay, now we got it. So it takes some time. So this is the PCA individual data point, okay? As you can see, these are all the data points, observations. And this is dimension 1, PCA. This is the first dimension, PCA. So it explains 83.9%. And this is the second dimension, is the 7.1%, right? This is the second dimension, right? So we want, if your data is close to this is 0 point, so which means that these data set does not make a contribution to make clear principal component patterns, right? So, but as you can see, okay, so 40%, so data point 40, so he has, look at this, so 35, his data point is very close to the dimension 1. So principal component 1 explains his data point perfectly. But second dimension does not explain his score, okay? So his score can be explained by principal 1, okay? But what about this? So 40. So his data is explained by the first dimension, and then also the negatively. This is negative sign, right? So his score is related to the second dimension as a negatively. Okay. So in that way, you can evaluate each data point on the PCA plot. But we do not want many data points close to this 0 point, origin 0, 0 point. Okay, if there are a lot of data here, which means your data set is not, is not appropriate for develop a PCA analysis. Okay, does that make sense? Okay. Right, so this is for individual, and then next we can also plot the variables using f visualization underbar PCA underbar variable function. We just same. This is our data, and these are all the. This is all the optional. So if you just remove this part, it will give you the all black dot. Okay, but I will add this one. So run it. Okay, now we get this PCA analysis. So this is the variable analysis. So we have dimension 1 and dimension 2. These are all variables, right? So which means, okay, hip and weight, right? These two variables can be explained by this line almost perfectly, right? So these hip and weight can be explained by the dimension 1. There is no dimension 2 here, right? So which means hip and weight, they have a same direction. So these two variables are very highly correlated each other. And also they are explained by dimension 1. Okay, and then thigh and bicep, their direction is pretty close, right? So these two variables are highly correlated, and also these two variables are correlated. Okay, so they are all correlated each other, and also it gives us the, for example, the biceps. The variable can be explained by the dimension 1, this much, right? But dimension 2, like this. So which means, okay, this bicep has explained by dimension 1 and dimension 2. But impact of dimension 1 is greater than dimension 2. Okay. So what if we have this kind of line here? If, let's say, bicep is here, which means this bicep variable is all negatively correlated with other variables because they have totally different direction, opposite, right? And then also this variable has negatively related to, because the direction is negatively related to the dimension 1, but dimension 2 is still positive, so positively related to the dimension 2. Any questions?
A quick question.
Sure.
If we have variables that aren't like numerical, they're instead like categorical, would we have to like transform them into like a kind of like a dummy code and then put them into vectors, or is that like a whole different separate kind of thing if you're looking at like categorical?
So you mean the categorical variable for PCA?
Yeah, is that even possible to do anything like that?
No, PCA analysis is for numerical variable.
Okay.
Yeah. So PCA analysis for numerical analysis, you can use the categorical variable for PCA. So, okay. And now you can plot both using biplot function. If I run it. Okay, well, it takes some time. Okay, now we got all the individual data points, and also we have some variable axis, right? So we can plot both. So, but interpretation will be same. Okay. All right. So any questions about the plot interpretation? Is it clear? This is fine? Okay. So what about the abdomen? So because it's pretty important to interpret your result. So I will copy and maybe I can paste it. All right. Okay, see. So this abdomen, right? So it has, this is the, look at the principal one. This is PC1, right? PC1. So his PC1 score is positive, right? So this score is positive, like this, the positive. So maybe 0.7 or something, let's say level 7. What about the PC2? This is PC2. His PC2 score is negative 0.3, maybe negative 0.3, right? So which means that this variable has positive relationship with the PC1 and a positive negative relationship with the PC2. That these values are magnitude of relationships. Okay. Okay, now let me go back to the run. And then now let's run. So we extracted the PC values, right? PC scores. Now let's use the PC scores to run the regression. Instead of using all the raw data, now we can run the regression using PC scores, right? So I just put the PC1 in the predictor and the data set. This is, I created this data set previously, and then you can run it. Run and run it. So now we can see, so this is a regression analysis, the PC1, and then it explains almost 89% of the total variance. So the PC1 explains so our regression analysis in this regression analysis. Okay, and then also you can add more PC values, right? So we had two non-significant coefficient, a non-significant relationship here. If I run this one, you can see this is dependent variable, and this is the PC values, right? So PC3 is very low correlation, and PC6 is very low correlation. So okay, maybe I can add more PC values to improve R score. So I just add 2, 4, 5 here, and then run it. Okay, yeah. So our R square is significantly improves, right? But how many PC scores do we need to use, right? Our main goal is to reduce the dimensionality. So are we going to use a 1 PC or 3 PC or 4 PC, right? So you have to make some decision, right? So, okay, so even though 1 PC is obvious, but it only explains 49% of the total variance in our regression model, maybe you could consider additional PC. Right? So, okay, so this is the principal component analysis, and then I just use PR comp function, but you can also run a principal component analysis using where is it? The print comp function. But print comp function is quite useful when you use correlation metrics or covariance metrics. Because so if you have raw data, that'll be great. But sometimes you only have correlation metrics or covariance metrics without raw data, right? In that case, you can still run the PCA using those metrics. So I created a correlation metrics here. So these are correlation metrics. So 8x8 correlation metrics. I run it, and then these are all the standard deviation information for each this is covariance matrix. So, and then I run it, and then using this package, you can convert the correlation matrix core to covariance metric to correlation matrix. Okay, so maybe I should change the cov. This is covariance matrix and standard deviation and the cov. And then now, okay, what is it? Oh yeah. And then cov, then this is covariance matrix, and then this is correlation matrix. Okay, this is correlation matrix, right? And then you can use, you can run principal component analysis using the correlation matrix instead of a raw data. Okay, using PrinComp function. Cov matrix is correlation. So, and then summary, so you can get this results. So comp 1 to comp 8, and these are standard deviation of each component analysis and proportion. Okay, so if you square the standard deviation of each principal component, that if you square it, that is the variance, right? So the variance of each principal component is what? That's eigenvalue. So if you square these scores, so that will be eigenvalue. Okay, and then get the summary. Oh, we got it. And then calculate the principal component, right? So scatter plot like this. So using PCA, using the plot function. Okay, this is another approach to run PCA using the correlation matrix or covariance matrix rather than the raw data. Okay, right. So far I showed you how to run the PCA from the variable extraction approach. Now I will show you how to select a variable from the variable selection approach. Okay, this is a backward selection regression. Okay, so first you need to create the model first. Okay, and then I entered all the predictors here, and then fit all. And then you have to put your created model, and then using the step function, and then direction is a backward. Okay, if I run it, so okay, it gives us some result. So as you can see, our starting point is our starting model includes all variables, right? So this is all variable included, and then this is AIC value, so model fit, and then it says, okay, if first chest variable is removed, what will be the AIC? 745.7. Okay, if hip variable is removed, what will be the AIC? Okay, in the same way, it removed every single variable and run regression and report AIC. Okay, and they always, the highest value produce the best model fit. Okay, because if you remove chest, so AIC is a 745. Original AIC is a 747, but it decreased. It's not much, but it decreased, right? So AIC is the model fit index. So we want a lower value. Do you remember? So the AIC value includes deviance. So we want a lower value. So okay, so chest is removed, and chest is removed, right? Here, there is no chest. And then we remove one by one, and then get the AIC value again. Okay, now hip. This variable, AIC is the previous AIC is a 745, it decreased. So we remove it. And then again, do the same again. And then now when we remove a biceps, so AIC becomes a 743.16, it's slightly decreased. right? So we remove this one. And then this is updated AIC value. And then now we stop. Because if we remove any variables, predictors, their AIC values will increase, right? So we stop here, and then this will be our final model. So, okay, from the backward selection method, the weight, abdomen, and thigh will be selected. This is a backward, and then this is forward. Forward is first. So I created the model, but our starting model is from 1 because this is only it only includes intercept. There is no predictor here. So this is our null model, right? And we start from the null model, and this is our data set. And then I will first start, I run it, and then in the step function, I put the data, and then direction equals forward, okay? And then you have to put this one scope. So it will, this will give you the forward, so the fit indices values. I think that this is, if you don't put this one, it will, yeah, it doesn't give you all the results for the forward method. So when you run the forward method, you have to add this one, scope is fit all, okay? And then if you run it, and then now we can see, right? So here, we start from the null model, only intercept is included, and this is our AIC value. And then, okay, first the predictor is added, and then our AIC value is a 780.74. It decreased a lot, right? But if we add the second variable, is the 898. So we select the first one, right? Because we can see the variable produced the most significant fit improvement. And then this is updated AIC value from here. And then we add another variables one by one and compute all the AIC. And then we select this one. Okay, this is a 780, but it decreased to 745. This is selected and do the same thing. And third one, thigh, is selected and then stop, because our AIC is a 743. But if we add the other variables, our AIC goes up. So our model fit gets poor. So we stop here. So this will be our final model. Okay. So we still have, luckily, we still have the same results, but you may have different results depending on the AIC, backward or forward selection. Okay. In this example, we still have the same variables to be selected, but it is not guaranteed. And then this is the stepwise selection. So simply, you can put both. Okay. It starts from the forward and backward, So it will see right here. So, okay. So it starts from the forward, right? So our null model, and this is AIC from our null model. And then we add every single variables, and then abdomen is selected. And then this is our updated AIC, and this is new model. And then we added every single things. And then we subtract this one again. Okay, so for the selection and backward selection, in forward selection and backward selection, once variable is included or removed, it will not be evaluated again. But the stepwise, they evaluate all the selected variable again. Okay. Anyway, do we have the weight variable improves the model fit the best, right? The most. So we select weight, and then weight is selected, and then we do that again. So add everything here, and then we remove, and it evaluate the fit again. Okay, now thigh is selected, and then thigh is added, and then we do add it, and then stop. Because every combination decrease our model fit, right? So our final model is abdomen, weight, and thigh. So luckily, we still have the same results. Okay, so this is the backward and forward and stepwise selection. But if you want to use this approach, I highly recommend you to use the stepwise selection approach. Okay, please do not use backward or forward, because like I said, once a variable is included or removed, they will not be evaluated again. Okay, so stepwise selection. And then now I'm going to show, this is the last. So the regression subset selection method, including exhaustive search. So the LIPS package will do this for you. Okay, so what is this? What does this do is this reg subset function, and then this is our dependent variable and our independent variable, and then it can it evaluates, and then you have to put exhaustive. It will evaluate all the model fit based on all possible combinations. Okay, so but you can say, you can simply put the number here, and best means, okay, best combination. If I put 1, that means, okay, I want to get the best regression line for each variable. So I will show you first. Run it and run it. Okay, so this is the first and sixth. So single predictor. Okay, when we include the single predictor, and the abdomen will be the most significant. If I add 2 predictors, that will be weight and abdomen. If I add 3 predictors, that will be weight, abdomen, and thigh. Okay, if I add the 4th, that will be this one, this one, this one, this one. Okay, so in that way, it will produce the every possible the combination of each the predictors, and then so you can also plot it using the subset function. It's like you need to install car package, and then subset function LIPS. This is we just run this model, and statistics. I will get the BIC here. So run it. So if you see, okay. So this is a subset size, and the first predictor. If you select only one predictor, A will be selected. If you select 2, W and A will be selected. If you select 3 with W, A, and T, 3 variables will be selected. Okay, so this is the exhaustive search process. It will run all possible combinations of regression and then give you the best solution for each predictor. Okay, and then, but I only searched the main effect, right? But if you want to add interaction effect, so you need to put this one. This is two-way interaction effect. If you put 3, it will give you all the main effect and two-way interaction and the three-way interaction solution. Okay. So yeah, if your number of variables are quite low, quite small, this may not be very useful. But if you have a lot of variables, this will be useful. Okay, so based on this result, that you can select, okay, this set of variables will be more influential than other sets. Okay, Okay, so this is for today. So today I showed you the how to run, PCA analysis using two different approach, pre-comp and also the PC comp. And also I showed you the variable selection method, backward, forward, and stepwise, and also exhaustive search approach using the reg subset function. All right, so any questions? I posted the R syntax and R the data set. So you can practice yourself. Okay. Right. So if you don't have any question, so I will stop here. Like I said, after everyone submitted the homework, then I will post the answer key to the Blackboard, so you can compare your answers with the key. Okay. And the next class, we'll learn about factor analysis. Okay. So mainly, I will focus on the factor axis factoring, principal axis factoring method. Okay, thank you. I will stop here. I will see you next week. Not next week, this Thursday.
Hey Phil, I wanted to just stay by for a quick second to ask you something.
Yeah.
So I guess it was like last semester, me and a couple of my classmates were running stuff for like a social robotics class, and it's been a long time, so I have to kind of remember what we